A child moved down a long slide as shown in figure 4.1. Nice. So our boy here is going to whee. So this kid here moves from rest at the top end of the slide, and we have resistive forces, 76 Newton, opposing the motion of the child as they move to the lower end of the slide. Okay, sure. Kinetic energy of the child at Y is 300 joule. So Ke here at Y is 300 joule. The decrease in GPE as it moves from X to Y is 3200 joule. Wow. Okay, let's see. When we travel from X to Y, we will suffer a change or a decrease in GPE. So change in GPE, which is negative 3200 joule, will convert to change in Ke. Since the child is at rest, meaning the Ke at X is 0. So the change in Ke is actually just positive 300 joule. Wow, teacher, the 2009, what happened? Where it go? Resistive force law. Resistance is a sneaky force. It will take away a lot of your energy, my dude. It's like waking up at 6 a.m. Hey, resistive force very big. Kinetic energy to come to class is very small. Okay, so the resistive forces here is work done against friction. Just what is left basically. So we have 2900 joule of what is essentially heat or wasted energy. The child's butt is going to be very hot. Friction. All right. So right now they want the ratio of the kinetic energy of the child when the resistive force is 76 Newton. So this 300 joule. And the kinetic energy of the child if there is no resistive force. Interesting. If there's no resistive force in an alternate universe, if there's no resistive force, then all the GPE will become Ke. So negative 3200 joule on one side, positive 3200 joule on the other side. No loss, no leakage, 3200 joule. So this is the ratio that we're talking about. We just need to write 300 over 3200. Which is 3 over 20, and then 3 over 32. This one is 0.09375. You could write that many SF if you want to, but I'm going to stick to 2, so this is 0.094. Okay? So no resistive forces, all the GPE will become Ke. That's why there is a negative sign. GPE is negative because it's to show that GPE decreases. Okay. The negative sign here is to show a decrease. Okay or not? All right, negative here because GPE is decreasing. I'm going to put a positive here to show that Ke is increasing. Heat energy also increasing. The butt is getting hotter and hotter. Increase. Okay. So that the equation makes sense. Of course, you could just choose to say 3200 is 300 plus 2900. Also can. I just want to add the sign there to remind my brain. Decrease. Hello, brain. Don't mess up the question for me. Don't make me lose my marks, brain. GPE decrease, Ke increase, heat increase, Ke also increase. Okay, so be very aware of the energy shift, the energy flow from decrease in GPE to increase in Ke. All right, moving on. Use the answer in A to calculate the ratio of the speed of the child at Y and the speed of the child at Y if there's no resistive force. Wow, ratio is also their best friend now. Very nice. So Ke is half mv squared. Okay, so I'm thinking to myself that this 0.094 is the kinetic energy when there's no when there is resistive force to when there's no resistive force. Okay, so let's write down this in a short form equation for now. This one, or rather 0.094 is equal to Ke with resistance ratio Ke with no resistance. Something like that lah. You write it in a way that you know what you're writing can already. Okay, so this is half m, the speed with resistance, divided by half m, the speed with no resistance, square. 0.094. So the half m and half m can go away. Okay, half m and half, because it's the same child, it will have the same mass. So what I now have left is 0.094, I draw a line here, is equal to Vr over the velocity of no resistance square. And finally, the answer will be square root of 0.094. I'm just going to write this one as the ratio that they want. So that would make my ratio to be equivalent to square root of 0.094, 0.30659. 66. Converting to 2SF, this is 0.31. Okay, so the 2 mark here, the first one is if you know Ke is half mv square. You write Ke is half mv square, we give you 1 mark. Okay, and then you substitute everything correctly, leading to the final answer. Root, this one is in. Of course, you could simplify your answer a bit. If you are my kind of student, you will think, teacher, Ke is half mv square. Same child, bo, same child. So Ke is proportional to v square. Which means the Ke 0.094 is equal to the ratio of velocity square. And then you can bring over and square root. But let me write another line here lah, for your brain a bit. So this one here, I can say Ke of r divided by Ke of no r is equal to velocity of r, velocity of no r square. Okay? So this part here can be done if you know what you're doing. If not, feel free to just substitute values carefully and do some manipulation, because we know the ratio of Ke. So we start with the ratio of Ke, use half mv square, simplify when needed to find the ratio that we want. Okay, 0.3. All right, that is part B. Part C, calculate the length of the slide. So if I think about my change in GPE, which is negative 3200 joule, decrease, all that energy is converted to Ke, which is positive 300 joule, and some of it is lost to work done against friction. If you can build this framework and you know what is going on, then they can ask you to find anything, you are okay already. So to find the length of the slide from X to Y, I need to consult how much work I need to do against friction. Because the further I travel, the more work done I need to do against friction. Okay, so W is equal to Fs. 2900 is the frictional force, 76, multiplied by the distance traveled from X to Y. So we can find S now. 2900 divided by 76, this is 38.157,894, 38.2, or to 2SF, this will be 38 meters. Right, this is 2 marks. So if there is 2900 here, or you draw this anything lah. Basically, you know how to use the conservation of energy. So if you don't want to draw this, you could also write this 2900 as 3200 minus 300. Okay, this part here, whether it's 2900 or 3200 minus 300 is 1 mark, C1. And then all the subsequent calculation is A1. Okay, so I hope you understand every question, right, starts off with a main idea. If you get the main idea right, then most of the time your answer will be right. But if you don't show the main idea, sometimes you may lose mark. So make sure to show either 3200 minus 300 or some form of flow chart also can. It also helps your brain organize. Okay, so try not to suddenly come up with a number like 2900 without showing how you get 2900. It's good because you imagine if let's say I'm doing this question with you and I just suddenly, ta-da, 2900, you know the meme with the butterfly, 2900. How teacher, how do you get 2900? I am confused. Okay, so as a pro tip here, always write down how you get new numbers. All right, so next part. The child is brought to rest by a board as shown in this diagram. So our child now, which has, I am going to assume that there's still friction. Okay, at the end of Y of the slide, the child is brought to rest by a board, as shown in figure 4.2. A spring connects the board to a fixed point, and the spring obeys Hooke's law, and has a spring constant of 63 Newton meter negative 3. So this spring constant here, K is 63 Newton meter negative 1. The child hits the board so that it moves to the right and compresses the spring. Speed of the child becomes 0 when the elastic potential energy of the spring increases to the maximum value of 140 joule. So we do have the maximum value of elastic potential energy. Calculate the maximum compression. So we could say elastic PE can be calculated using the equation half. Look, I have K. I don't have the force in the spring. I could maybe find the force, but I couldn't be bothered, so I'm going to use half KX squared. Okay? You can use half Fx, but we don't have F. So use K, because K is given to you. Can you use F is equal to Kx to find X? Can. But extra work lah. I don't like to do extra work unless there's a reason to. So we're going to find the maximum compression, X squared. This is 140. Okay? So from here you can find X. X would be 140 times 2 divided by 63. And this is, wow, 4. Okay, hang on. Square root factor. 2.10 meter. Okay, because it's Newton meter. So not a very hard spring, not gonna lie. 2.1 meter. Okay. Calculate the percentage efficiency of the transfer of the kinetic energy of the child to the elastic potential energy of the spring. Sure, don't have 100% transfer, man? No. Remember at Y, your KE is 300 joule. Then, KE at Y is 300 joule. And then after that, it collides with the spring. Now, spring, so where is Y? Let me look at the spring first. Okay, this is the surface of the slide. At the end Y, there is a board. Okay, that means the board is here. And the spring is here now. Okay, so at Y, there's 300 joule. But unfortunately, the spring only receives elastic PE of 140 joule. So we know the boil will slow down, right? because the spring is slowing it down. And the kinetic energy of 300 joule, and if you are following generally my sign convention, I will either write kinetic energy is 300 at Y. This one is at maximum compression. So I can write it this way if I don't want the negative sign, or I could just say change in KE converted to change in elastic PE. Elastic PE rise by 140. KE drop by 300. Wait a minute, there is missing energy. Correct. Heat, blame friction again. Friction will suck away 160 joule. Friction will suck away 160 joule. Okay, so if I put change, it is helpful for me to include the negative sign to show me that that 300 will drop, 140 will go to elastic PE, 160 will be lost to heat. So this one is lost to friction. Friction steals your energy. So to find efficiency, I will take 140, so transfer of kinetic energy, 300 kinetic energy to elastic potential energy, 140 times 100. This is 47%. Okay, so efficiency is the energy that I can get back. Whatever that is lost as heat, 160 joule, I cannot get back already. All right, part 3. The maximum compression of the spring is x0. On figure 4.3, sketch a graph to show the variation of elastic potential energy to compression of the spring, where this is x0. So your x0 here is your 2.1 meter here. So the elastic potential energy starts off at 0 because there's no compression, and it will end at 140. 140 joule. Question. Straight line or curve? Straight line. Curve like this, decreasing gradient. Curve like this, increasing gradient. 1, 2, and 3. So to answer this question, you can refer to the equation of elastic potential energy and displacement. Okay? So elastic potential energy is equal to half kx square. Now you see the square here. So this square basically tells me that it has to be quadratic or basically a curve. 2 is out. Now which curve are we talking about? The elastic potential energy is again positive. So this one would be positive x squared. So you will get a shape that looks like this. Increasing gradient. Let me draw it a bit better. Increasing gradient. Okay? Because the change in EPE is positive. Or you can say, let's say I look at the fx graph. There are a few ways to look at it. Okay, fx graph is like this, right? Straight line. So let's say I stretch the first distance here, which is here. This area is work done. So this value here is W1. Area here is W1. This W1 is kind of small. Yes. Compared to, let's say, I take a section towards the back. About the same width. Okay. So towards the back here, about the same width, maybe here. This area is much bigger, right? This area here is W2. Where is W2? ... This one. W2 is here. Your increase in energy. Of course, your W1 will be smaller than your W2. That's why your gradient is getting steeper and steeper. So the increase in this tiny bit of area will be a slow climb. Towards the end, when the spring is harder to compress, you will store more energy. So here this is W2. So the area under this is actually elastic potential energy. Area under Fx is equal to elastic PE. So greater extension, W2, when you compress towards the final field Cm, you will store the most energy, so the gradient is the biggest compared to the initial pressing. When you initially just starting to press the spring, it is very soft. Okay, so these two mark here. M1 mark is curved line from 0, 0, because initially the spring is not compressed. A1 mark is there is an increasing gradient. So if you draw straight line, you will get 0 mark. Okay. If you draw curve, you can get 1 mark. If you curve in the correct direction, then you will get second mark. But there's positive here. So basically what we're looking for is positive x squared curve. That's why I include a positive sign here. If you need to. If you don't need to, you can always think about how when the length is short, first few meter or first few cm, less energy stored in spring, okay, compared to the last few cm. The work done increased a lot. The area of trapezium here very big compared to the triangle. Okay, so this is your question 4.